Good morning. Today we start with fluid kinematics, fundamental of flow visualization. While quantitative study of fluid dynamics requires advanced mathematics, much can be learned from flow visualization. The visual examination of flow field features. Flow visualization is useful not only in physical experiments but in numerical solutions as well. Computational fluid dynamics CFD. In fact, the very first thing an engineer using CFD does after obtaining a numerical solution is simulate some form of flow visualization so that he or she can see the whole picture rather than merely a list of numbers and quantitative data. Because the human mind is designed to rapidly process an incredible amount of visual information, as they say, a picture is worth 1,000 words. There are many types of flow patterns that can be visualized, both physically and or computationally. So this is a spinning ball. So in the wind tunnel at the University of Notre Dame, here the flow speed is about 77 feet per second and the ball is rotated at 630 rpm. Streamlines and streamtubes. A streamline is a curve that is everywhere tangent to the instantaneous local velocity vector. So this is streamline here. You can see this is the velocity vector. This is velocity in vertical direction. This is velocity in horizontal direction. Streamlines are useful as indicators of the instantaneous direction of fluid motion throughout the flow field. For example, regions of recirculating flow and separation of a fluid of a solid wall are easily identified by streamline pattern. Streamlines cannot be directly observed experimentally except in steady flow fields in which they are coincidence with pathlines and streaklines. To be discussed next. Mathematically, however, we can write a simple expression for a streamline based on its definition. So consider an infinitely arc length dr. So this is your dr. It is equal to dxi plus dy plus dzk along a streamline. Now take a local velocity vector, that is v, which is ui plus vj plus wk by definition of the streamline. By simple geometric arguments using similar triangles, we know that the components of dr must be proportional to those of velocity. Hence, so this is almost, so means dr by v is equal to dx by u is equal to dy by v is equal to dz by w, where dr is the magnitude of dr and v is the speed. The magnitude of v. Now streamline in xy plane. Say we take the xy plane. Now what is streamline? That is dy by dx along a streamline is equal to v upon u. So if you take this dy by this dx, that is v upon u in xy plane. For the simplicity, we won't consider here z plane. We are taking only x and y. A streamtube consists of a bundle of streamlines, much like a communication cable consists of a bundle of fiber optic cables. Since streamlines are everywhere parallel to the local velocity, fluid cannot cross a streamline by definition. So these are the streamlines and this is your streamtube. A streamtube consists of a bundle of individual streamlines. By extension, fluid within a streamtube must remain there and cannot cross the boundary of the streamtube. You must keep in mind that both streamlines and streamtubes are instantaneous quantities defined at a particular instant in the time according to the velocity field at that instant. In an unsteady flow, the streamline pattern may change significantly with time. Nevertheless, at any instant in time, the mass flow rate passing through any cross-sectional slice of a given streamtube must remain the same. For example, in a converging portion of an incompressible flow field, the diameter of the streamtube must decrease as the velocity increases so as to conserve mass. Likewise, the streamtube diameter increases in diverging portion of an incompressible flow. Pathlines. A path line is the actual path traveled by an individual fluid particle over some time period. So this is your path line. Fluid particle at starting, fluid particle at some intermediate time, and fluid particle at end. A path line is formed by following the actual path of fluid particle. Now imagine a camera with the shutter open for a certain time period, that t start, time and t end, in which the particle's path is recorded. The resulting curve is called a path line. An intriguing example is shown here in this figure. Neutrally buoyant white tracer particles. So these are neutrally buoyant white tracer particle, means they will remain at the same position where you will left them. So the result is path lines that are elliptical in shape, showing that fluid particles bob up and down and forward and backward, but return to their original position upon completion of one wave period. There is no net forward motion. You may have experienced something similar while bobbing up and down on ocean waves. A modern experimental technique called particle image velocimetry, PIV. So this is PIV applied to a model car in a wind tunnel. Utilize particle path lines to measure the velocity field over an entire plane in a flow. In PIV, tiny tracer particles are suspended in the fluid, much like in figure 421. However, the flow is illustrated by two flashes of light, usually from a laser as shown in figure 422, to produce two bright spots on the film or photo sensor for each moving particle. Then both the magnitude and direction of velocity vector at each particle location can be inferred. Means with the help of this camera, the photography is done and you can measure the velocity vector at each particle location, assuming that the tracer particle is small enough that they move with the fluid. Modern digital photography and fast computers have enabled PIV to be performed rapidly enough so that unsteady features of flow field can also be measured. So you can see a dye or smoke will enter from this side. This is the fluid will flow and these particles are injected at time. Here 8 particles injected with the time, and we will assume that they will follow the same path as your fluid will follow. Path lines can also be calculated numerically for a known velocity field, especially the location of the tracer particle is integrated over time from some starting location x start and starting time t start to some later time tracer particle location at time t. So x is equal to x start plus integration t start to t velocity dt. So here you can say initial position of particle is given, tracer particle. When you integrate from t start to time with velocity dt, you will get the position at different interval of time. So this equation is calculated for t between t start and t end. A plot of xt is path line of the fluid particle during that time interval. For some simple flow fields can be integrated identically. For more complex flows, we must perform a numerical integration. Now what is streakline? A streakline is locus of fluid particles that have passed sequentially through a prescribed point in the flow. Streaklines are the most common flow pattern generated in a physical experiment. If you insert a small tube into a flow and it produces a continuous stream of tracer fluid, dye in a water flow or smoke in air flow, the observed pattern is streakline. So this figure is showing streakline. As the particles are forced out of the way by the object, they accelerate around the shoulder of an object. You can see this is the wing of a plane. So when the particle will strike, it will come into their path. So they will accelerate in this direction and they will change their path. The streakline is formed by connecting all the circles into a smooth curve. In physical experiments in a wind or water tunnel, the smoke or dye is injected continuously, not as individual particles, and the resulting flow pattern is by definition streakline. So means here you have to give the particles continuously to this stream. The particles will go and they will take their positions with respect to time. Then we will take a frame for those particles, and this frame shows these streak lines. Now don't get confused with streak line and these streamlines. Streak lines are often confused with streamlines or path lines. While the three flow patterns are identical in steady flow, they can be quite different in unsteady flow. The main difference is that a streamline represents an instantaneous flow pattern at a given instant in time, while a streak line and a path line are flow patterns that have some age and does a time history associated with them. So whatever photograph is taken, it is taken after some time interval, while on the other hand, a streamline is a curve that is everywhere tangent to the instantaneous local velocity vector. So it is measured instantaneous. So a streak line is an instantaneous snapshot of a time integrated flow pattern. Means after some time this picture is taken. A path line on the other hand is the time exposed flow path of an individual particle over some time period. So in path line a fluid particle will flow, and for the particular time interval we will connect all the positions, and then we will get a path line. So a path line is found by following the actual path of a fluid particle over a time interval, that is t is equal to t start or t is equal to t end. The time integrative property of streak lines is vividly illustrated in an experiment. The author used smoke wire for flow visualization in a wind tunnel. In operation, the smoke wire is a thin vertical wire that is coated with mineral oil. So this is a smoke wire which is coated with mineral oil. The oil breaks up into beads along the length of a wire due to surface tension effects. When an electric current hits the wire, each little bead of oil produces a streak line of smoke. When multiple streak lines are introduced along a line, as in figure 425, we refer to this as the rake of streak lines. The Reynolds number of the flow is rho Vd upon mu is equal to 93 because of unsteady vortices shed in an alternating pattern from the cylinder. The smoke collects into a clearly defined pattern called a Karman vortex streak. So one may think that the shed vortices continue to exist to several hundred diameters downstream of the cylinder. However, the streak line pattern of this figure is misleading. The smoke wire is placed 150 diameters downstream of the cylinder. The resulting streak lines are straight, indicated that the shed vortices have in reality dissipated by this downstream distance. So in this case, you can see a smoke wire located at a x by d 150. The time integrative nature of streak lines is clearly seen by comparing the two graphs. The flow is steady and parallel at this location, and there are no more vortices. Viscous diffusion has caused adjacent vortices of opposite sign to cancel each other out by around 100 cylinder diameters. The pattern of figure 425a near x by d is equal to 150 are merely remnants of the vortex streak that existed upstream. The streak lines of figure 425b show the correct feature of the flow at that location. The streak lines generated at x by d equal to 150 are identical to streak lines or path lines in that region of the flow state, nearly horizontal lines, since the flow is steady there. Now if you have to find the location of tracer, that can be found out by x injection where you have injected the tracer plus integration of where you have injected to the present velocity with respect to tt time. So this will give you the tracer particle location. So this is about streamlines, stream tubes, streak lines. Like this channel, subscribe it, and thank you for watching.